In this video tutorial, we'll examine the procedure to generate a path loss. To begin with, I've loaded the vector measurement file located in the advanced data directory called dipole.dat. Once loaded, I recalled the data from Reg 1, which transferred it into Reg 0, making it the active data that we'll be working with. We click the Generate Path Loss button to launch the path loss module. It should be noted that the button will not be green unless the path loss has already been generated, which we have done here. This module allows the user to select their desired unit of measurement and includes inches, feet, miles, centimeters, meters, and kilometers. Once a unit of measurement has been selected, that unit will become the default throughout all of the path loss module. This is especially handy in the simulator where dimensional links are in terms of paths. In this case, the measurement was made from 2 to 3 GHz. The array is filled with the path loss data, which includes one data point for every frequency step. This allows us to see, for example, that at 1 meter, the path loss varied from -38 to -42 dB per inch. At 1 meter, the gradient sensitivity is 0.2 dB per inch. So if you have some sort of a path error, this can help determine the error associated from the dB per inch. In addition to specifying the separation distance, you can also use the group delay. When using group delay, we must specify what the as-L settings are. In this case, I'm going to go ahead and do an auto scale. What results is a mean path of 1.5 meters with a min gain of 1.2 dB and a max gain of 2.1 dB. The peak gain with this antenna was approximately 50 degrees elevation. This enables you to get a feel for your measurement. While the measurement was at 1 meter of separation, the phase of the reference horn and the associated cable was not included, hence it comes out greater than 1 meter. Upon exiting the group delay module, the mean value will be inserted into the path as its distance. Another option is to specify a fixed path loss value. If the path loss value was set at -10, then the path loss value will be at -10 in all as, L, and frequency. Another option is to use the laser bore sight tool, which allows the laws of cosine to be evaluated numerically. So essentially, you employ the measurement scale at the right angle to the reference antenna and you employ the rotational accuracy of the platform with the laser. If the platform has moved 5 degrees plus or minus and the distance of D1 and D2 are noted, the resulting path distance and the pointing angle are calculated. There is a small ideal calculator so you can establish the range, the angle, or the D figuratively or exactly. The last option is the gradient tool, which enables you to change the position or settings to allow you to make 3 associated measurements, one at a time, with each measurement associated with the movement of the reference antenna, 1 path forwards and 1 path backwards. After that is complete, the gradient is calculated and compared to the ideal. If you have not prepared the data properly, you get this message. The ideal gradient is 8.68 dB per unit of path. The result is that the valid frequency points over distance are plotted, and the gradient is plotted in terms of min-max. The result in the gradient path calculation, the min-max value can also be used, as well as the max value. One thing that is notable about the gradient method is that the real path can be determined between the phase points over frequency. So, if properly performed, the real path as well as the frequency dependence will result. And this concludes our video tutorial on the path loss module. If you have any questions or comments, please feel free to email us or give us a call. We hope this video has been helpful and informative. Thanks for watching.